Okay, before we continue with the work energy theorem, we take this point in the class to digress a little bit, and we introduce you to a very important example of a non-constant force. Specifically, it's the force acting on a mass due to a spring. So I have right here, for example, an ordinary spring like so. I'm going to go ahead and attach it here vertically in this manner. Then I'm going to take a mass here, attach it to the spring like so, and then I'm just going to release it from rest. And then this extremely important type of motion that the object undergoes is what is called an oscillation. Oscillations occur throughout nature, and they also occur throughout the technology that we have and the engineering that we have. For example, oscillations are a starting point when it comes to any sort of clock that you may use to keep track of time. Oscillations are also the starting point when it comes to specific types of electrical current, that is, alternating current. The alternating current that comes out of an ordinary wall socket, for example, is described by an oscillation. Oscillations are also the starting point for anything associated with waves, whether it be waves on a spring, water waves, seismic waves, sound waves, and even light itself. Ultimately, it's all begun to be described by an oscillation. Okay, now getting back to this actual oscillator itself like so, you can see immediately, of course, that the acceleration of this mass is definitely not a constant. So then therefore the forces exerted upon it due to the spring, that also has to be non-constant. So let's go through a basic description here of the spring force. Okay, let me go ahead and detach this like so. I'm going to tilt my camera towards the board. So bear with me as I do this, like so. Okay, and then let's begin to write out the description here of the spring force. Okay, so we have a very important example. Of a non-constant force. And that's the spring force. Okay, first of all, a couple of things about the spring itself. The spring is considered, for now, to be idealized. It's an idealized spring. Now that means a couple of things. For example, we consider the weight of the spring, we consider its mass to be negligible compared to the mass that is attached to it. Now, of course, that's not really the case. If I hold it here horizontally like so, it sags under its own weight. If I hold it vertically, it sags under its own weight. We ignore that completely. We consider the spring's mass to be negligible. Okay, secondly, we also ignore or don't take into consideration any differences between stretching and compressing the spring. We treat those situations as identical. Now, of course, in reality, they're not. Let's say, for example, that I hold the spring like so, and if it's not stretched or not compressed, this is referred to as the spring's equilibrium position. The spring, by the way, is an example of an elastic object. If I then take the spring and stretch it out from its equilibrium position like this, you could see that I could stretch it out quite a big distance. However, I am constrained by the coils of the spring itself from compressing it all that much, for example, like so. We ignore this difference between stretching and compressing completely. We consider the situations to be physically identical. So, secondly, there is no physical difference between stretching and compressing the spring from its equilibrium position. Okay, and then third, Whenever in reality you take an elastic object and you disturb it from its equilibrium position like so, for example, imagine doing something like this with a rubber band and then touching the rubber band afterwards, well, you may have noticed that the object itself heats up. In essence, some of the energy that I'm using, for example, to stretch the spring back and forth is being converted into heat due to the molecular interaction that takes place within the spring. We ignore this completely. We assume that there is no heat generation. In addition to that, by the way, because I'm using a metal spring here to demonstrate, I'm actually generating radio waves when I do this. Think of that as another form of heat. We ignore all of that completely. So we consider the heat loss to be negligible. Later on, when we study oscillations in detail, we'll actually then take into account the heat that is lost as the spring stretches and compresses, but for now, we do not. We ignore the heat that is generated. So we'll ignore heat loss as the spring is stretched and compressed. Okay, so taking into account these idealizations, here's then how I'm going to describe to you the spring force. I'm essentially going to lay it all out here on the board for you, and then I'll go back to the side here and demonstrate what it is that I'm about to describe. Okay, so let's erase all this. Okay, what I'm going to do in just a few minutes as I demonstrate this is I'm going to take the spring and I'm going to hang it vertically from my attachment like so. Now in reality, the spring of course does sag a little bit under its own weight. We ignore that completely. So then therefore this is the unstretched or uncompressed position of the spring. We call this point right here, for example, the equilibrium position. Okay, and then what I'm going to do is I'm going to take a mass M and attach it to the spring, and then I'm just going to let the spring dangle down vertically. I'm not going to set it into oscillation. When I demonstrate this for you in just a few minutes, the mass that I'm going to use is going to be this object right here. We're going to consider this object here to be a mass M. Okay, so now attach M and just lower vertically. So it's not in oscillation. Therefore, it's going to look like this. So right here is my mass M attached to the spring. Right here, once again, is the equilibrium position. I'll be displacing the spring downwards some distance from equilibrium. This displacement from equilibrium, like so, is referred to as x. Okay, now because the object is not in oscillation when I do this in just a few minutes, the acceleration is going to be equal to 0. Therefore, the forces acting on the mass cancel out. There are two forces acting here vertically. So for example, we have the weight mg like so, and then we have the spring force upwards. Let me refer to it as F spring. Because the acceleration is 0, those two forces are equal to each other. So in other words, we know what F spring is equal to in this situation. It's just equal to the weight mg. And then what I'll do is I'll detach the mass m, and I'm going to reattach to it another object, this object here. This object here is twice as massive as this object. So then therefore this one here is referred to as m, this guy here is 2m. As you'll see when I do demonstrate this, we'll then stretch out the spring a greater distance from the equilibrium position. So now what I'll do is attach to it. Once again, I'm not going to let it oscillate. The acceleration will be 0. That will then look like this. So here's the spring like so. Okay, once again, drawing it the same way, right here is the equilibrium position, and then this right here is our mass 2m. You'll see that I will in fact displace the spring a greater distance from the equilibrium position. Let's refer to this displacement right here as x prime. Once again, however, the forces acting on the mass, in this case 2m, just cancel out. So then therefore, off to the side, here's a force diagram to represent that. We have 2mg downwards like so for the weight, and then we'll have the spring force upwards, which I'm going to refer to here as F spring prime. Okay, the two forces cancel because once again the mass will just be sitting there. The acceleration is equal to 0. So then therefore I can write F spring prime is equal to 2mg. So by attaching an object that is twice as massive as the first object, notice that what I have done here is I've doubled the spring force. F spring prime is twice as much as F spring. So then therefore, F spring prime is twice as much as F spring. Right off the bat here, we're seeing one of the empirical properties associated with the spring force. The greater the amount that you stretch or compress the spring from its equilibrium position, the greater the spring force. And I can feel that, for example, here in my right hand when I stretch out the spring. As I stretch out the spring a greater distance from equilibrium, the amount of force that the spring is exerting upon my hand back towards the equilibrium position is obviously increasing. Therefore, right off the bat, here we get an understanding as to why eventually when the object oscillates, the spring force is not a constant. The spring force itself depends directly upon the displacement from the equilibrium position. It's actually quite easy to see the relationship between the spring force and the displacement from the equilibrium position if you now watch this as a demonstration. So let me re-tilt my camera back towards my attachment here. So bear with me as I do. Like that. Okay, now let's take a look at the entire scenario here as a simple demonstration. All right, so right here is the equilibrium position of the spring. Remember that we're considering this right here to be the unstretched or uncompressed position of the spring. Once again, we're ignoring the fact that the spring does in fact sag a little bit under its own weight. So right here is the equilibrium position. Okay, and then right here is the mass M, like so. Attach it to the spring, and I then displace the spring this distance x here from the equilibrium position. Once again, the object is not in oscillation, the acceleration is 0, so then therefore the mg straight downwards and the F spring upwards cancel each other out. So F spring here is equal to mg, and then we have the displacement x like so. Okay, now I'm going to go ahead and detach this guy, and then let's go to here. This is the mass 2m, and now let the mass then displace the spring from equilibrium. This distance here is x prime. Notice that it's greater than the original value of x. Once again, however, the object is not in oscillation, so the F spring prime upwards is being canceled out now by 2mg downwards. So what I have done here is I doubled the spring force by doubling the weight of the object that is attached to the spring. But as I said a few moments ago, there's a simple relationship between the displacement from the equilibrium position and the spring force itself. It's easy to discern that relationship if you watch the entire demonstration occur in sequence. So now watch this again. All right, so here's the mass M, and then here's the displacement x like so. Here's the mass 2m, and then here's the displacement x prime. Right here was the original x a moment ago. Right here is x prime. What do you suppose the relationship is between x and x prime? Obviously, x prime is twice as much as x. What this means is that the spring force is directly proportional to the displacement x from the equilibrium position. Because what I've done here in this demonstration is I've doubled the spring force. In order for that to happen, you have to double the displacement from the equilibrium position. There's an easy way in which we write out this empirical relationship associated with the spring force. This empirical relationship is referred to as Hooke's law. It's named after Robert Hooke, who was a contemporary of Isaac Newton in England in the late 17th century. Okay, let me go ahead and tilt my camera back. Like so. Okay, so what I've shown here in this demonstration empirically, if I could spell it, is that x prime is equal to 2 times x. That's what you saw in the demonstration. So what this then means then is that therefore the spring force is directly proportional to the displacement from the equilibrium position. So if you double the displacement from equilibrium, which is what I did, you then double the spring force. If you triple the displacement from equilibrium, you triple the spring force, and so on and so on. So there's a direct linear relationship between the two. Now, when quantities are proportional to each other, this then means that there is a coefficient or a number that is present here that turns this into an equal sign. This coefficient is referred to as the letter K, and it's called the spring constant. It's essentially an empirical measurement of how stiff or how loose the spring is. We write out the relationship in the following way. As I said, this is known as Hooke's law. F spring is equal to, in magnitude, K times X, where K is called the spring constant. You'll eventually measure it, by the way, in a mini lab exercise in the future. And the spring constant is an empirical property of the spring. It is measured in terms of newtons per meter. And it's essentially a measurement of how stiff or how loose the spring is. Or loose the spring. So let me demonstrate that to you with a couple of different springs. Once again, I'm going to tilt my camera back. So bear with me here as I tilt the camera once again. Like so. Okay, now I'm not going to use this large demonstration spring here for this purpose. Instead, I'm going to show you two other springs. So right here, for example, is a really loose spring. This really loose spring right here has a really small spring constant. In part, the properties of an oscillation depend upon the stiffness of the spring, depends upon the spring constant. So for example, if the spring constant is very small, as it is here, watch the effect that this has on an oscillation. So right here is a small object like so. Then I'm going to go ahead and attach to this spring in this manner, like that. And then I'll set it into oscillation like so. And you can see immediately that the time necessary here for one oscillation to occur, which by the way is also called the period, is in fact rather long. Now compare the time necessary for an oscillation here to the time necessary for an oscillation to occur with this spring. This right here has a really large spring constant. This right here is a very stiff spring, and now what I'm going to do is I'm going to attach the same mass to that spring, like so. And then watch how quickly the oscillations here occur, like so. So in this particular case, the period associated with the oscillation is much shorter than it was for the other spring that I used a few moments ago. So in part, the properties of an oscillation do in fact depend upon the spring constant. Eventually, as I said, you'll measure the spring constant in a short mini lab exercise. Okay, let me conclude this portion of the lecture involving the spring force here.